Hello everyone, my name is Serge Znikian and welcome to my presentation today. Imagine a disease that nearly infects 250 million people every year and killing over 600,000, mostly young children from Africa. And this isn't science fiction, this is malaria. For decades, we fought it with powerful drugs, our best weapons, but we're facing a crisis. The parasite is evolving, it's learning to survive our treatments, and we're losing it. Malaria is caused by a tiny parasite called Plasmodium falciparum. It's carried by mosquitoes, and our main defense is a class of drugs called artemisinin-based combination therapies, or ACTs. And these were miracle drugs, and they were saving millions of lives. But here's the problem: evolution. Just like bacteria evolve resistance to antibiotics, the malaria parasite is also evolving resistance to artemisinin and its partner drugs. And it started here uh, in Southeast Asia. And really alarmingly, we're now seeing the first clear signs of resistance in Africa, the continent bearing the heaviest burden. But why is this happening? Tiny changes in the parasite's DNA mutations in genes like PFCRT or PFK13, it allows it to survive treatments. And when resistant parasites survive, they really multiply and spread. The resistance isn't just theoretical, it has devastating real-world consequences. Treatment starts failing more often, people stay sick longer, the disease spreads further, and tragically, more people die. And right now, our global strategy is largely reactive. We wait until we see like widespread failures in clinics, then we scramble to change like treatments and put like guidelines. By then, the resistance parasites are already deeply established, and we're always one step behind. This reactive approach isn't sustainable, and we need to get ahead of the curve. But what if we could anticipate where resistance is likely to emerge or explode before it happens? But what if we could use the parasite's own evolution against it? This brings me to our idea supported by the Gates Foundation Challenge. We propose to integrate real-time genetic tracking of the parasite with evolutionary computer models to predict resistance hotspots and design smarter, proactive drug strategies. Think of it like weather forecasting, but for drug resistance. We know resistance isn't random. It's driven by predictable forces, the parasite's existing genetic diversity, the pressure we apply with drugs, and how parasites move between regions. But how do we do this? First, we go to the front lines, places like Burkina Faso and Cambodia, where resistance is really known place and like where emerges the threats. Second, we use portable DNA sequencing technology devices like small enough to potentially use closer to the field. And we rapidly analyze the genetic code of malaria parasites from patient samples. And we look for those known resistance mutations and potentially new ones. Third, we combine this genetic information with data on which anti-malarial drugs are being used in those specific areas. And finally, we feed all this data into evolutionary computer models, and these models simulate how mutations might spread under different conditions, and which allows us to identify areas at high risk and the emergency hotspot and test in simulations which drug strategies like rotating drugs or using different combinations might be most effective at slowing down evolution in that specific location. Why is this so important? Because getting ahead of resistance means our current drugs remains effective for longer. It means fewer treatment failures and reduced transmissions and ultimately lives saved. It really allows us to move from a reactive one-size-fits-all approach to really better proactive strategies that are informed by local evolutionary dynamics. It means using our precious anti-malarial resources more intelligently and sustainably. This isn't just about fancy technology, it's really about applying fundamental evolutionary principles to really address and solve this pressing global health crisis and making sure treatments keep working for the vulnerable population who really needs them most. The malaria parasite is really a master of evolution that But evolution works by predictable rules, and by understanding those rules and using modern tools to track the parasite in real time, we can really anticipate the next move, and we can design smart interventions, and we can choose all smart evolution. Thank you.